So I'm going to talk a little bit and maybe ask you guys some questions along the way. There's no problem just shouting things out or answering things that are kind of wrong, or you're like, it was kind of like this, and not really knowing the right vocabulary. I don't expect anybody to remember really anything in great detail. Okay? So trigonometry is going to be the focus for this semester. When you look at the word trigonometry and you look at the prefix or the root word for this, what do you think? What do you see as a prefix or root word?
Ooh.
Yes, sir.
Try, like 3.
Yeah, so you see try, 3, or if you thought maybe trig, you might think triangle, right? And that's really kind of the building block of this course for trigonometry is the triangle. Okay? So if you think back to geometry, and I know that was a long time ago and some of us have varying levels of memory of what we did in geometry, but we should remember triangles was something that you spent a good deal of time talking about. Does anybody remember any facts about triangles past they have 3 sides?
3 types.
Okay, so there's some different types of triangles. When you say 3 types, do you remember any of them?
Scalene, equilateral, and isosceles.
Okay. So these are the ways you can classify triangles based on their side lengths. You could also classify them, though, based on their angles. What are the 3 there?
30, 30, 60.
So 30, 60, 90 is a special kind of triangle, but it's...
Right, obtuse, and I don't know if they're...
Anybody?
Oh, acute.
Acute, yeah.
QT.
So acute, right, and obtuse were the ways that you could classify them based on their angle measures. Right? So acute has all angles less than 90 degrees. Right have one angle equal to exactly 90 degrees. And obtuse have one angle greater than 90 degrees. Scalene has no congruent sides. Isosceles has at least 2 congruent sides. And equilateral has 3 congruent sides. Good. So that's good. What else do you guys kind of remember? Yeah, go ahead.
All the angles are for the same number.
Yeah, the sum of the interior angles should equal 180 degrees. Very good. Absolutely.
Area is 1/2 base times height.
Okay. Cool. Okay. Any others that we can think of off the top of our head? Not a big deal if you can't. We'll fill in some other stuff that I want to talk about that's more directly related to where we're going. But this is a good start. So one of the most important ideas that you talk about in geometry are these 2 relationships called congruence and similarity. Right? We say 2 figures are congruent if all the side lengths are congruent and all the angle measures are congruent. And we say 2 figures are similar if all the angles are congruent and all the side lengths are proportional. So what do we mean by proportional? So like if we have 2 triangles like this, and this is like 2, 3, well, I shouldn't say that. That's an impossible triangle. Let's do 3, 4, 5. That one's real. This one then would be like, could be like 6, 4, 10, where the other triangle is just twice the side lengths of the other one, right? Everything is in the same proportion. Is everybody okay with that? We'd say that these 2 triangles are similar. And that's a really critically important concept from geometry that should ring some bells. Again, I don't expect you to have complete mastery of it. I don't expect you to have remembered it without me kind of jogging your memory on it. But it should at least at this point like go, okay, that sounds familiar. And for sure, you probably did some similarity proof at points during geometry or did some calculations to show two things were similar. The other thing, the other piece of this is going to be these three functions called sine, cosine, and tangent. Do you remember talking about those? Usually we use the acronym SOHCAHTOA to help us remember the relationship between those functions, sine, cosine, and tangent. So what SOHCAHTOA, or how we define sine, cosine, and tangent in our geometry class is, okay, we said we had a right triangle. And if we look at one of the acute angles for the right triangle, that if I find another right triangle that has the same acute angle in it, then like the ratio of side lengths, these must be similar because of angle would be the similarity theorem you'd use to show those are similar. Not important that you remember what that means. But those ratios of side lengths need to be equal because the triangles are proportional, right? And what we said then is, okay, well, I can create a function then, in this case it was tangent, that maps that acute angle measure to that specific ratio of side lengths for any triangle, any right triangle that has that acute angle measure in it. So that's what these sine, cosine, and tangent are doing. So the SOHCAHTOA here is just describing how we find those ratios. So once we've identified the acute angle we're working with, we name the side lengths based on the location of the acute angle. So the hypotenuse is always the longest side of the triangle. The adjacent side is the other part that makes up the acute angle that's not the hypotenuse. And the opposite side is the one that's left over. So when we say SOH from SOHCAHTOA, that says that sine theta is equal to opposite over hypotenuse. Or when we say CAH, that tells us that cosine theta is equal to adjacent over hypotenuse. Or when we say TOA, that says that tangent theta is equal to opposite over adjacent. And this is probably where you guys left off in a traditional geometry course, would be as far as you guys kind of got, were the right triangle definitions for sine, cosine, and tangent. Now, this is basically where we're going to pick up in this course. So the idea here is currently these sine, cosine, and tangent are tied to right triangles. What we're going to spend the majority of our time first semester doing is extending these definitions so that we're not relying on a right triangle. Because right now, our values for theta that I can use in sine, cosine, and tangent are just stuck between 0 and 90 degrees, right? So if you took the honors geometry course at some point, you would have seen that, okay, we can extend our definitions for sine and cosine so that they can be between 0 and 180 degrees using the law of sines and the law of cosines. It's not important what you know, that you know what those two things are right now. We'll certainly spend time in this class talking about that, as I would expect most of us would be seeing that for the first time. Typically not a part of the traditional geometry curriculum. But even better, we'd want to extend this to include angles that cannot possibly be part of a triangle. So if we think back to our geometry class, if I have an angle that looks like this, the angle measure that we're talking about is always this red distance, right? It would never be that distance, right? That's how we defined what an angle measure would be in geometry. Now, there's real life situations where that green measurement might be more useful. So let's imagine this. Let's say that we're trying to navigate something. So we're flying a plane or piloting a boat or even just like walking through a field, like somewhere where there's not a grid road system laid out. And we're trying to describe to somebody how we go from one place to another. Left-hand turn, right-hand turn make little sense now, since there's no grid. There's no roads to follow. You can kind of go wherever you want. So we need to have some way of describing, say, how we get from this location to like this location. Well, you could certainly turn that many degrees to get there, right? And then to get back, you have, if you wanted to go back to the starting location, you could either turn the opposite direction or continue turning the same direction that far, right? Now, if we're going to be communicating with somebody, it's going to be much easier if we've agreed on that, like, hey, when I say turn this many degrees, we're always talking about turning to the left that many degrees versus, okay, then turn this many degrees to the left and then turn this many degrees to the right, and then, you know, where it's constantly like, which angle am I talking about? We're going to just agree that like everything is going in one direction, makes life considerably easier to communicate with one another. So that's a situation where all of a sudden this angle that's kind of an impossible angle in geometry becomes something that we would really be interested in, right? If you're turning that far on piloting a ship or a plane or a boat or whatever. Is that okay? So that's the next step, is to, okay, we'll want to extend this so that we can have angles between 0 and 360. Right? Or you can do like a full turn or whatever.
Mr. Coolin,
Yes.
why do you put the dash between the zero, the second zero?
Oh, that's the symbol theta. This is the, like, it's a variable.
Oh, so it's not even like a zero? It's just,
Yeah, so it could be like, you think of an X there. Yeah. So typically in a trigonometry class, we use like Greek letters like theta or alpha to represent angle measures, and then we use like our English letters like A, B, C to represent the side lengths. You know.
Oh, okay, that makes sense.
Now, not always, but kind of traditionally, that's kind of how that works. So that's why that theta is not a zero with a line. I mean,
Okay.
It looks like a zero with a line
Yeah,
through it, but
okay,
yeah.
makes sense.
Now let me give you another scenario, again, a real life scenario. Let's say you have a machine that has a part that spins on it. So like if you have a car, the drive shaft of the car spins and that supplies, you know, the spin to the wheels and makes your car go in a really simplified fashion. And I want to see how many times that drive shaft spins in a second. If you're talking about more than one revolution, that's basically an angle that's bigger than 360 degrees, right? And if your car, if in drive, your drive shaft spins this way, and you change and put it in reverse, what's going to happen? They'll spin the other way, right? So if we think about one direction of spinning as a positive angle, the other direction of spinning would need to be a negative angle. So that's the next thing we're going to do, is we're going to extend this definition further so that we can have angles that are bigger than 360, and we can have angles negative. So basically what we end up with is a definition of sine, cosine, and tangent where that theta, the input, the angle that we're taking sine, cosine, and tangent of, can be any real number. And that's kind of what the first half of first semester is kind of dedicated to, is taking these definitions of sine, cosine, and tangent that we developed in geometry and extending them so that they work in settings that they did not from a strictly geometric standpoint. Now, I haven't discussed at all how we're going to do that. And that's really going to be many days of lecture to kind of do that and work on, okay, so like if we think about it this way, what does that mean? And then let's do some practice problems where we're using this kind of a definition and blah, 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 and like really kind of dig deep and analyze this stuff. But I think it's really helpful at the beginning to get a picture of like, okay, where are we starting? Where are we starting at? What are we trying to do? Like, where are we trying to get to? And we'll fill that in kind of throughout the rest of this, or the first half of this semester. Now, the second half of first semester and the beginning of second semester, we're going to look at some systems that kind of operate the same way as what we developed here. So if you do a good job in the first half of first semester, the things in the second half of first semester and the first half of second semester are really kind of all the same problems. They're just framed under a different context. So everything is going to kind of work the same way as it did. It's just going to be like a different framework. So things should potentially get easier for you because it's still the same kinds of things that we've been doing over and over and over again. And then the second half of second semester is some review and extension of ideas from Algebra 2. So, like we'll redo logs and we'll redo, rational functions and some of these things that we did in our Algebra 2 course. With a little bit more stacked on it, but most, like 80% of it is still the same ideas. Okay. I'm going to stop here because I think we have just like 5 minutes remaining or something, which feels like not